Today we're going to be learning about independent events. So before we get started, let's take a deep breath. All right, now in our last lesson, we learned about things called dependent events and about something called conditional probability. And you may remember that the notation for that was we would do something like the probability of A given B. And the idea was that the probability of A may be impacted by whether or not B has happened. Today, we're going to be learning about a specific classification of events, which means some events are this and some events are not. So a classification of events called independent events. So again, as you're going through probability, you're going to find that some events are independent and some are not. And today's lesson is kind of all about what those are and how we tell whether or not they're independent. So I want to start with a definition here, right? The definition of independent events are that two events are said to be independent if the occurrence of one of them does not impact the other one. In other words, whether or not one of them happened doesn't really change the probability of the other one happening. Now, the significance of this is when two events are independent, there are two different things that we know. Okay, so I want us to look at this and think about this again. Remember what this means. And if you need to, pause the video and think for a moment about what this means. This is supposed to mean the probability that A happens given that B has happened, okay? But if these events are independent, it means that their probability shouldn't affect one another. And what that means is, it means that the probability of A happening given that B has happened, that should be the exact same thing as the probability that A happens, because B has no impact on whether or not A happens. Okay, so when events are independent, it basically means that the conditional probability is the exact same thing as the full probability of A. Okay, and this can also be said the other way around. When two events are it's not like A can be independent of B, but B can be dependent on A. That doesn't happen. Okay, so you can also say it the other way around. That the probability of B given A, well, B given A means the probability B happens given that A happened. Well, if it doesn't matter whether or not A happened, that would be the same thing as the probability of B. Okay, I know that was a lot of words that I was throwing out there. If you need to, pause and go back and listen to that again. This is sort of the first important component of what it means to be independent. Now, there's a second thing that we know when two events are independent. Okay, I hope you remember from the last lesson, we learned that the probability of A and B is equal to the probability of A times the probability of B given A. This was sort of the formula that we learned last week, the last time that we did this lesson. But when events are independent, remember that this probability changes, or rather it doesn't change. This probability is the same as the probability of B. Right? And so what it means is when we have independent events, we get a slightly different formula for the intersection of two events. So these two things are effectively properties of independent events. And what I want to do next is sort of talk to you about how we're going to use those properties and the ways that we may use them as we go through problems. So because the concept of independent events is effectively a property of events, it means that there are really two different categories, two different ways these questions can be asked, right? The first one is that you can be asked to show that two events are independent. So you could be given two events or two probabilities or information about a thing, and they can say, hey, we want you to show that these things are independent. The second way that independent events can show up in a problem is that you can be told that two events are independent, or you can infer that two events are independent and use that to sort of get you extra information in the problem so that you can find something else that needs to happen in the problem. And the reason that I talk about these two things is that it changes the way that we use those properties that we just talked about on the previous page. So to be very clear, when you are asked to show that events are independent, it means that you need to show these things are true. Specifically, it means that you can't use these properties, right? You have to use other methods, other tools, other diagrams to show that these things are true, because your job is to show that the events are independent. Okay. On the flip side, if a problem tells you that they're independent events, if it's given to you that these events are independent, then you need to use these things to show other results. And that's going to sort of depend on what the question is asking for. So independent events ultimately revolve around these properties, and it's a question of whether you're going to show these properties or whether you're going to use these properties. So now we're going to go into some examples of these things so that you can sort of see how this plays out in problems. So in this first example, I want to show you what it looks like when you need to show that two events are independent. So you're going to be given other information and asked to show that it's independent, show that the events are independent. So in a survey, it's found that 60% of students like pizza and 30% of students like cookies. Those, I don't know if those seem accurate, but that's what the problem says. We're then told that 28% of students don't like either of these things. Show that a student liking pizza does not impact whether or not they like cookies. So if it does not impact it, it means that these events are supposed to be independent. But remember here, we're being asked to show that they're independent. So it's good that we recognize that wording means independent, but we need to show that they're independent. Okay. So what I'm going to do now is I can't use those formulas that I just had. I'm going to need to show some of those things. So in particular, I'm going to try and show that the probability of, I want to try and show that the probability of pizza and cookies is equal to the probability of pizza times the probability of cookies. That's what I want to show. Okay, so let's see if we can get to that somehow. This problem feels like a Venn diagram is going to be useful. We've got two different events, some probabilities. There's a kind of a don't like either of them. So let's see where we get with a Venn diagram. So if I were to build a Venn diagram here, and I make this one pizza and this one cookies, okay? Remember from our previous lesson on Venn diagrams, we were just told that this entire circle is 0.6, 60%. I don't like to put that inside of the circle because you might confuse whether or not it's just for the crescent or whether it's for the whole thing. So I usually write that right on the outside, kind of up next to the label that I have. We also know that the probability of them liking cookies is 0.3. Okay. And then we've got this other piece of information. It says 28% of the students don't like either of them. So where would that go in this Venn diagram? Well, if they don't like either of them, it means that 0.28 is out here. Okay? Now, if I've got 28% that's out there, think about how we can use that. There's a really, really important way that we can use that piece of information. Really what it comes down to is if I do 1 minus 0.28 and get 0.72, that 0.72 is going to be all of this. That's going to be the OR probability of these things. Okay? So then remember that we have the little formula that we use for this, right? The probability of pizza or cookies would be the probability of pizza plus the probability of cookies minus the AND probability. Okay? We just found out that the OR probability is 0.72. The pizza probability was 0.6. The cookies one was 0.3. And I don't know what this one is, but we're going to find out in a minute. These two things combine to be 0.9, and so when I subtract that over, I'm going to wind up here with 0.18 equals the probability of P and C. Okay, so I've just found out that this thing is true. Okay, now in order to show that these are independent, I would need to show that the AND probability is equal to the two probabilities multiplied together. Well, take a look at it. If I do the probability of P times the probability of C, I'm going to get 0.6 times 0.3, which is 0.18. And then we might write something like, because these two things are equal, we say that the events are independent. So this is one example of what it can look like to show that events are independent. You notice we needed to use other tools, other diagrams, other things to show that one of those properties of independent events was true. So here's my second example type. In this one, you're going to be told that events are independent, and you're going to need to use that to do other things. So example says, consider independent events M and N with the probability of M being 0.4 and the probability of M or N being 0.8. Okay? So for part A, find the probability of N. So you'll notice here that we're given this OR probability. Right? So if we're given an OR probability, the first thing I think of is, hey, I have a formula for OR. Right? Our formula for OR is supposed to be that the probability of M or N is, and you should actually make sure that you remember what this formula is on your own, it should be the probability of M plus the probability of N minus the probability of the intersection. Okay. So now I could go back through this and say, well, all right, I know this is 0.8, and we know that this is 0.4. Unfortunately, I don't know what the probability of n is, so that's a bummer. And you might over here be sad, like, oh man, I also don't know what the intersection probability is. And this is where independent events comes in. Because these events are independent, what do we know about the and probability? Well, the property that we just learned is that this and probability right here is supposed to be the probability of m times the probability of n. Okay, but we don't know both of those things, but we know that the m probability is 0.4, and the n probability is the thing that I'm trying to find. Okay, so at this point, notice that I had a formula that had 4 different unknowns in it, and now it turns out that there's only one unknown. It's just this probability of n I don't know, which happens to be part A in the problem. It's very common in IB problems that the first question will sort of set you up to find something that you need. So let's go ahead and move through solving this thing. If I move this 0.4 over, I'm going to end up with 0.4 equals, now here I have probability of n minus 0.4 probability of n. That's going to become 0.6 times the probability of n. And if you weren't quite following why that happened, the idea here is that this is really 1 p of n, and then this is 0.4. This is almost like 1x minus 0.4x, and that's why I'm getting this 0.6 probability of n. And then I just need to divide this thing over. So when I divide that over, I'll have 0.4 over 0.6 is the probability of n. And this is basically 2/3. I could do it as like a 0.6 repeating, but that's effectively going to reduce down to 2/3. So now that we have this, now that we've finished part A of the problem, we're going to move on to part B. Part B says we want to now find the probability that n occurs, but m does not. Okay. Now, this might be a little bit hard to see, but that's basically an and probability. Think for a minute about why that's an and probability. Okay. It's an and probability because you're being asked to find the probability that n occurs and also that m does not occur. Okay? But again, these are independent events, and so because they're independent events, we can use the properties of independent events to say that this has to be the probability of n times the probability of not m, and then I just need to plug in these values that we have. We just found that the probability of n was 2/3, and the probability of not m, well, if the probability of m was 0.4, it means the probability of not m would be 0.6, because they have to add up to 1. So here, I would probably want to write that as like 6/10, and then we could reduce this. So this would be a 5, this would be a 2, so it looks like this is 2/5. I'm really hoping that this one made sense. This is, again, an example of when you're given that events are independent and you're being asked to find other things. So you're going to use those properties that we learned previously. Sometimes the problem won't say that events are independent because the events are clearly independent, and you're supposed to sort of imply that. Examples of events like these are dice being rolled, coins being flipped, and cards being drawn from a deck with replacement. It's really important that the cards are replaced because otherwise when you take a card out, it's going to change the probability of the other things. In general, you should not use independence if the events sound like they're independent. You know, if it's something like, oh, the probability that it rains today and the probability that I eat pizza for dinner, there may be a thing there. You may need to show independence on that. You really only want to assume independence when you have sort of like disconnected information here. When you roll a die, if you get a 6, that doesn't change whether or not you're going to get another 6. Okay, so let's go into this next example. A fair 6-sided die is rolled 3 times. Find the probability of rolling a 5 or higher all 3 times. Okay, well, since these are dice, and it's not like the dice can remember what they rolled last time and they try and avoid it the next time, all I need to do is multiply probabilities together here. The probability of rolling a 5 or higher, if we think about rolling a 5 or higher, let's see, that would be rolling a 5 or a 6. So there's basically a 2 in 6 chance of that. So that's a 1 in 3 chance. So if I wanted to get that to happen all 3 times, I would need to roll that, and that, and that. So this probability ends up being 1 out of 27. This ends up being really quick. What I'm really doing here is I'm using that property, the probability of A and B is the probability of A times the probability of B. When you have independent events, if you want to know what the probability of an and thing, of something and something and something, all you have to do is multiply their probabilities together. I hope that one made sense here. For our last example, I wanted to do something that had a little bit more going on with it. So a fair six-sided die is rolled 5 times. Find the probability of rolling a 6 at least once. There's a really big clue here. When this thing says at least once means maybe I roll 1 6, maybe I roll 2 6s, maybe I roll 3 6s. That's a lot of things that are going on. Lots of times in probability, you want to find a way to sort of simplify the problem. Okay, so if somebody said find the probability of rolling a 6 at least once, kind of the opposite of that, the complement of that would be rolling no 6s. Okay, and so I guess my thinking on this problem is if you want to find the probability of rolling a 6 at least once, it might be easier for us to do 1 minus the probability of rolling no 6s at all. Okay? And maybe another way of thinking about that is that this could be the probability of rolling all 5 dice to be less than 6. And so at this point, this problem should be fairly similar to the last one. I want you guys to pause the video and sort of think about that, see if you can come up with this one on your own. Well, to get something that's less than 6, that means I would have 5 chances out of, 5 positive outcomes out of 6 total. And I would need that to happen all 5 times. So I'm hoping that you guys saw this as like 5 sixths times 5 sixths times 5 sixths times 5 sixths times 5 sixths. And then you're going to need to do 1 minus that. So when I used the calculator for this, I found this to be 1 minus 0.402, which means this whole thing winds up being 0.598. So this is another sort of show of how we would use independence. And I mentioned on the previous slide, one of the big things that comes out of independence is that when events are independent, you can just multiply their probabilities together if you need to have multiple things happen. So if you have a long string of ands, you can just multiply those independent probabilities together. So I hope this has all made sense and that you guys will do really well in the example problems. If you have any questions, make sure you send them over to me so I can help out.